So the binomial identities that will start with let me just get, okay. So we already described this or defined this as n factorial over r factorial n minus r factorial. So we define this as that so that it becomes so easy for us now to work with most of the identities. The first one being n r minus 1 plus n r is equal to n plus 1 r. So I want to show that the left hand side is equal to the right hand side. So the proof of this picks one side and shows that it's equal to the other side. So we'll pick the left hand side. So n r minus 1 plus n r. This is equal to n factorial over r minus 1 factorial r minus 1 multiplied by n minus r minus 1 factorial plus n factorial r factorial n minus r factorial from the normal definition of the factorials. Okay, from there we'll say, okay, this is equal to, we simplify further, so this is equal to still n factorial on top over r minus 1 factorial and then n minus r plus 1 factorial. So you understand that when you expand here, you have n minus and plus. The negative one becomes positive. Plus, this one just drop it the way it is. R factorial, n minus r factorial. And this is a very, very simple proof. And the basic of it is on the next step. This step here. If you understand the next step, then you understand the whole proof. So you want to get the common denominator here. So what do you do? Now remember that by definition we said r factorial can be written as r minus 1 factorial. From the definition of n factorial, be written as n n minus 1 factorial. We agreed that you can write it in any way, provided that wherever you end, you put a factorial. So if that is the case, when we get here, we can see that we have r factorial this side. We also have r minus 1 factorial this side, meaning that between the two, r factorial is bigger than r minus 1. Since we can write r factorial as r multiplied by r minus 1 factorial. So between this and that, our common denominator will be r factorial. Now we can choose to write this as r minus 1 factorial. So the same thing happens to the other. The same thing happens to the other. Instead of us writing it as, you've seen we have n minus r plus 1 factorial. This can be written as, if you take this whole thing to be one thing, so if you take n minus r plus 1 factorial, you discover that you have n minus r plus 1 multiplied by n minus r factorial. Since we subtract a 1, so when you subtract a 1 from n minus r plus 1, you remain with n minus r factorial, meaning that between this and this one, we would pick n minus r plus 1 and write it in the form this. So write it, this guy is the same as this, so we'll take it in this form and then open up there and say we're now dividing. So when you divide by r minus 1, the r will remain, and then this whole thing is just the same as that denominator there, the other piece. So we just multiply this by n factorial. Since we said this thing which I've written there is the same as this, which we have on top. So plus the r factorial is just the same as this, so there's nothing there. Then the n minus r leaves this part here. So we have n minus r plus 1 multiplied by n factorial. Again, n factorial is common, so you can factor it out. N factorial is common. We've remained with r plus n minus r plus 1 divided by, we now want to write this as just r factorial because it's indeed r factorial. And then this whole thing as just this because they're the same, n minus r plus 1 factor like that. And then our next step will be, that is just n plus 1 multiplied by n factorial. Since r minus r is 0, so we have n plus 1. So you can put it in front of n factorial, and then we have r factorial. You can write it as n plus 1 minus r factorial, but this is just n plus 1 r, which is our right hand side. So it's that simple there.
I haven't understood. Can you please go back to how you came up with the denominator?
Okay.
And then
So,
has two, sir.
hello.
And the how we're dividing to get the denominator.
To get the numerators. Okay. So, and this is the basic identity that you need to understand. I'll be very, very slow here and very, very generous. So I go back nicely. We'll get here again, don't worry. So we go back. We want to come up with a denominator again. And the numerator again. And how we simplify nicely. So I remove this, I will write. This is in favor of those who just joined and those with questions. May we please understand this thing so that our children will have easy understanding as well. Okay, so we are saying by definition r factorial is the same as r minus 1 factorial. If you have where there is r here, suppose where there is r we put n minus r plus 1. This thing can also be written as n minus r plus 1, first thing. Following it will be n minus r plus 1 minus 1. And a factorial outside. But if you simplify, you understand that you have n minus r plus 1 multiplied by 1 minus 1 is 0. So we'll get n minus r factorial. If this thing here took the place of r, you would put it there and subtract a 1. Just like we have put it here and subtract a 1 from it and then put a factorial. Just like we were solving, if you are given to solve 7 choose 3, we were saying this is 7 factorial over 3 factorial. 7 minus 3 would be 4 factorial. And then we are reducing 7 up to 4 factorial because we've seen it down there. Now my point is, since we are able to reduce and when we decide like we should end, we just put a factorial, we can do the same reduction here. For as long as when we decide to end, we subtract, we put a factorial. That's how we have this factorial coming in down at the end and having everything reduced there in that manner, so that when we go to our fractions here, we want a common denominator. So between r minus 1 factorial and r factorial, you can see that in r factorial, there is actually an r minus 1 factorial. So we'll get the bigger one. R, we can even write it as r minus 1 factorial. R factorial can be written as r minus 1 factorial. Since they are the same here, we can do the same to n minus r plus 1 factorial. You can write it in this form. N minus r plus 1 multiplied by n minus r factorial, and then divide. R minus 1 factorial divided by, R minus 1 factorial divided by r minus 1 factorial. You can see that we have r remaining. This piece here is what we have here, which we have defined in this form, and this is what we have taken here. This means that we'll have r and n factorial just on this part, plus r factorial in itself, we get 1, and n minus r factorial in this whole thing, it will only take away this. It will only take away this piece, the r will remain. So we have n minus r plus 1. So we have n minus r plus 1 multiplied by n factorial, the numerator. So that n factorial is common, we can factor it out from the numerator and remain with r plus n minus r plus 1 over, since we chose to write this r factorial in this form, we can decide to rewrite it as just r factorial. And since we chose to write this to represent this here, we can choose to write it as n minus r plus 1 factorial, giving us n plus 1 in the brackets there. It is just n plus 1, since r minus r is 0, and then there will be an n factorial down, up there, so that we divide then by r factorial n plus 1 minus r factorial. But this is how we define n, because this on top there, that numerator there, this numerator here is just the same as n plus 1 factorial, exactly the same as n plus 1 factorial over r factorial n plus 1 minus r factorial, but this is just n plus 1 r factorial. You understand that the definition of this, if we tried to reduce the right hand side here, would have gotten n plus 1 factorial over r factorial, and the next thing would have been n plus 1 minus r factorial, which is exactly what we have here. That's why I've defined it that way.
Excuse me, sir.
Yeah.
So, like the way you've done it, like, so if I was taught to prove this identity, then I go with the right hand side, then with such a from that step where you need up at n plus 1 over choose r, then ukushafe direct kuri yoyo mwalemba po pamoja ti abashania.
If you get this and write it in this form, is it? For it to be equal to the left hand side, you must be able to separate it. Excuse. You must be able to separate it and write it in this form. When you are told to prove, someone must not assume for you to say you would have gotten here. No. To prove it, it must be clear that you have reached there. Like it is here. We are sure that we have reached. And for sure we have reached it here. No assumptions that maybe 2-3 steps from here they would have gotten there. Then you're given full marks. No. And in most identities, you can't just pick any side. Some sides are more simplified that you can do nothing to it. So this is just one of them. We still have a lot coming.
So, Basa, what you mean is identity.
Yes. You got the most complicated one to get the simplified one. Now look at this one. Look at identity number 2. NR is equal to N minus R. Proof. You can see at the left-hand side it is more simplified that you cannot do anything to it. So let's pick our right-hand side, which is N minus R factorial. What is happening? This is equal to N factorial over N minus R factorial N minus R factorial. But this is just the same as N factorial N minus R factorial N minus N plus R factorial. But this is N factorial. So as you can see that all we are doing, we just placed using the definition. The remaining thing is expanding the brackets there and follow it. Now what is N minus N? N minus N is 0. So in the whole brackets there I've remained with R factorial. But the other one, N minus R, is still there. But this is what we have here. This is what we first record. That is the definition of NR. So we have N R factorial. So this is our left-hand side. If you want, as you start to prove, you first reduce each side. You say this is N factorial over R factorial N minus R factorial, and this is N factorial over N minus R factorial multiplied by N minus R factorial. You first reduce each by one step, then you pick the right hand side. You can't take them at once, like this side is moving, the other side is moving, then you say the ends they are equal. You pick one and so that you can get to the other. So some can be this easy and some can be this complicated. So if you invest your time in the easy ones first, they will guide you on how to get to the hard ones and get them. But one thing you must know is that all these identities, they are based on common definitions, like the definition of N factorial, which we define as N minus 1. Just knowing, being able to know that if I decide to end here, I can put a factorial. That's the key thing of all these identities. If you know that you can redefine n factorial in that form where you are free to go down, but the time you decide to end anywhere, you put a factorial, then everything becomes easy. If it is R factorial, you must be able to extend the definition even to other letters, where you say I can decide to end here. Even if they bring R n plus 1 factorial, I can redefine this as n multiplied by n plus 1 minus 1 and decide to end at n factorial. You can do that. I mean, this should be n plus 1. If you're able to understand this, that then this will just become n plus 1 multiplied by n factorial, then your life will be easy in this thing. If it's complicated for you, whatever you see inside here, like the other thing was where we had n plus 1 minus r factorial, you can start by saying, okay, let p be n plus 1 minus r, so that here I deal with p factorial and say that I can write it as p minus 1 factorial. But what is p? P is n plus 1 minus r factorial, meaning where there is p, I'll have n plus 1 minus r. Where there is p, I'll have n plus 1 minus r. I mean, then I'm subtracting a 1 from it. So you subtract a 1 from it. Then it will guide you and be able to see that this is just n plus 1 minus r multiplied by n minus r factorial. You can easily see that. Another one. So we have two identities this far. The third one, we must show that n.
Sir, can you go back on the previous board?
Okay.
Just a bit.
Okay.
On the first one, is that a 2 on n factor? No. The other one. Not the first one, the third one. On the first one. There up at top of the first one. Is that a 2? N minus 2?
Yes. Yes.
Okay. All right, so thank you.
Okay. Okay. Okay, so verify that NR, so another identity, show that NR is equal to this. Now here we're just trying to verify. So we've now gone back to the binomial theorem, which we said it's a plus b to the power n, and giving us n choose 0, a n, giving us n choose 1, a n minus 1, b, giving us n choose 2, a n minus 2, b2, giving us n choose 3, a n minus 3, b3, going n choose r, a n minus r, br, keep going. So the task is we want to show that this coefficient here can actually look like this. Now you saw that when we attempted to solve for n choose 0, that day what came out was 1. Then we did n choose 1, what came out was n. Then we did n choose 2, what came out was n minus 1 over 2 factorial. Then we did n choose 3, what came out was n minus 1, n minus 2 over 3 factorial. What this means is that if we do n choose 4, what will come out is n minus 1, n minus 2, n minus 3 over 4 factorial. If we try n choose 5, what will come out is n minus 1, n minus 2, n minus 3, n minus 4 over 5 factorial. This means that if we keep going until we get to nr, what should come out is n minus 1, n minus 2, n minus 3, n minus 4, n minus 5. We can keep going until we get to n minus r plus 1, so that our down term should be less by 1 from the from the r minus 1 term, so that here we have r factorial, which is our right hand side of the top part there. So you can see that this is the left hand side we have on our equation, and this is our right hand side on our equation. The only required section here is to be able to create this pattern. You start with a 1 with n, it builds to 2 factorial down, to 3 factorial, to 4 factorial, to 5 factorial. As you build, you are seeing that for you to say 2 factorial is n minus 1. If I subtract 1, I can have 2 down. If I subtract 2, I can have 3 down. If I subtract 3, I can have a 4 down. If I subtract 4, I can have a 5 down. So what we are doing on the last term here is we are subtracting, for it to look like this, we are subtracting r minus 1. Okay, a smaller term. Now, if you're subtracting r minus 1, it's true that 4 is the same as 5 minus 1. 3 is 4 minus 1. 2 is 3 minus 1. 1 is 2 minus 1. That's why we are justifying now to say, okay, if we expand the brackets here, where there is n minus r minus 1, if you expand the brackets, we are going to have something else. What we'll have is r here plus 1, and then we have the r factorial down. So for this one can only come out using a pattern, and then you can extend your pattern to the generalized thing. There's a question from David.
Yes, sir. So, are we supposed to end there on n minus 5? Or since it's saying n minus 1, n minus 2, we should end up to 2 and put n minus 1 or n minus r plus 1 over r factorial?
It actually doesn't matter. Those dots there are telling that you are free to put anything that you want for as long as you get to the last one.
Oh, okay, sir.
Mhm.
Thank you.
Then the fourth one, the fourth identity would be NR R minus 1 plus 2 NR plus N R plus 1 is equal to N plus 2 R plus 1. Show that this is equal to that. You can't even start the right hand side. It doesn't, it has done nothing to us. The only thing which looks like it's a culprit is the left hand side. So we get the left hand side and try to reduce it. So the first part will be n factorial r minus 1 factorial n minus r minus 1 factorial plus 2 n factorial r factorial n minus r factorial plus n factorial r plus 1 factorial n minus r plus 1 factorial. Or if we want, we can first say we are reducing both sides so that we can know what we should expect on the right. So it is n plus 2 factorial that we should expect to see for us to say we have found the solution. N plus 1 factorial n plus 2 minus r plus 1 factorial. I think this will be simplified further together. So we'll have n factorial over r minus 1 factorial and then n minus r plus 1 factorial plus 2n factorial over r factorial n minus r factorial plus n factorial r plus 1 factorial. This is n minus r minus 1 factorial. So kindly mute n plus 2 factorial over r plus 1 factorial, and then this will be n plus 1 minus r factorial. Okay, so we can leave it here and now pick the left hand side. So when we see something like this, it will mean that we'll be done. Now look at our left hand side. It needs a common denominator. So let's see the common denominator that is coming out here. Between r minus 1 factorial, r factorial, and r plus 1 factorial, we can see that the highest number here is going to be r plus 1 it will be r plus 1 r plus 1 factorial. Since we can write r plus 1 factorial as r plus 1 multiplied by r plus 1 minus 1 multiplied by r plus 1 minus 2 factorial, but this is the same as r plus 1 r and r minus 1 factorial. So you can see that in r plus 1 factorial we have r factorial, because if we wanted would have just ended on the second position where we say this is r plus 1 multiplied by r factorial, or ended on the third one like here, so that it cannot take care of that. So this expression take care of this, and then the original one take care of the r plus 1. So we have r plus 1 representing all the r's here, then multiply by n minus r plus 1 factorial to represent itself, to represent this if you subtract 1, and to represent this if you go as far as 2, because even it, we can write it as n minus r plus 1 factorial. This is the same as n minus r plus 1 multiplied by n minus r plus 1 minus 1 factorial, but this is the same as n minus r plus 1 multiplied by n minus r factorial, so that it can take care of itself and this part. The other one, you can write this as n minus r plus 1, n minus r plus 1 minus 1, n minus r plus 1 minus 2 factorial. So this can be written as n minus r plus 1 multiplied by n minus r multiplied by n minus r minus 1 factorial. So that you can see that this piece here is represented in this denominator. And then let's see now what remains. So on the left, you've seen that r plus 1, r minus 1, we only remain with r plus 1 multiplied by r. So this part only will be taken away, and this one will remain. Then we'll multiply by n factorial plus the middle part, r factorial, will have r plus 1, and for n minus r plus 1, this piece will be cancelled, this one will remain. So we remain with n minus r plus 1 and then 2n factorial plus the other one, r plus 1, is taken care, which is just itself there. Then the other one, only this piece will be taken away. This whole piece here will remain. So you have n minus r plus 1 multiplied by n minus r which is being multiplied by n factorial on top there. Now we need to simplify here. So in our simplification, the denominator won't be touched because this denominator here is what we have here on the right hand side. So everything we do must end in the numerator there. So let's see what happens now. Okay. So the denominator as it is factorial, we can even write it now in this form so that it looks exactly like what we have written on the right hand side. Here n factorial is common and we'll have r. So let's what's the easiest way now here? Expanding. Okay, let's write it first. It will tell us what to do. Plus r plus 1 n minus r plus 1 plus n minus r plus 1 n minus r, but in the middle part there's also a 2. Now I've seen that in this form nothing looks like can be cancelled, so I thought maybe there could be something similar, but it looks like there's nothing similar. We have to do a normal expansion. So we have n factorial kept, or let's just pick what is in the brackets and then we'll come back to fit it here. So we have r plus 1, we have r plus 1 multiplied by r plus 2 plus 2 r plus 1 n minus r plus 1 n minus r plus 1 plus n minus r plus 1 n minus r plus 1 being multiplied by n minus r. So we are saying we want to expand this so that maybe it can guide us on what to do. In fact, we can do this in a quite a smart way. Between this and this one, if we factor out r plus 1, you notice that we'll have r plus 2n minus 2r plus 2. Okay, let's see if something can simplify here. The 2n. Okay, but the other one can simplify. Or it's also similar because of the 2 there. So let's just expand. So we have r squared plus r for the first one. And then we'll have 2 rn minus r squared plus r plus n minus r plus 1 plus n squared minus nr minus nr plus r squared plus n minus r. This is r squared plus r plus 2rn minus 2r squared plus 2r plus n, plus 2n minus 2r plus 2 plus n squared minus nr minus nr plus r squared plus n minus r. So we come now to cancel. So we'll have r squared plus r squared, we get 2r squared, which takes away the 2r squared negative there. Then minus nr takes away the 2nr. Then 2r minus 2r will disappear. What else? R minus r will go. We've remained with only a few things. We've remained with n squared, this one, plus n, this one, plus 2, this one, plus 2n, this one. Okay? But this can be written as n squared plus 3n plus 2. With product, this is a quadratic product 2, sum 3. So we can have n squared from here plus n plus 2n plus 2, giving us n plus 1 plus 2, n plus 1, so that we get n plus 1, n plus 2. So this means that when we go back here, the inside, so we'll start by writing the inside, and we'll write it in the form n plus 2, n plus 1. So same thing, so we'll have n plus 2, n plus 1, n factorial over r plus 1 factorial n plus 1 minus r factorial. But if you look closely, a product written in the form n plus 2, n plus 1, n factorial, this guy is the same as if you say p, then you say p minus 1, then you say p minus 2 factorial, you can write it as p factorial. Okay, so if p is equal to n plus 2, you can see that here we have n plus 2, then n plus 2 minus 1, then n plus 2 minus 2 factorial. This will be n plus 2. N plus 2 minus 1 is just n plus 1. N plus 2 minus 2 is just n factorial, telling us that this guy is just p factorial, which is just n plus 2 factorial. So let's go back where we have n plus 2, n plus 1, n factorial. This is just the same as n plus 2 factorial over r plus 1 factorial n plus 1 minus r factorial. But this is what we have on the right hand side, meaning that this guy is actually n plus 2, choose r plus 1, which is our right hand side. Hence proved. So you have to show the working. So this page is part of your working. Oh, I thought that was a question. David.
Sir,
Hello.
sir, how often does it come in the exam?
It comes maybe once in 10 years. So you don't need to worry much for some theorems, but the exam is a composition of simple and hard stuffs. So if you have given so many simple things, you may decide to put a hard stuff to compensate the time on those simple stuffs. And if you have observed in most exam papers, you'd find that there were questions that if you solved it, it would have taken you longer. So sometimes the way they put questions is, you can find that where this question is, let's say it's on question 1. Question 1 has A, B, C, and D. So you'd find maybe question C is saying complete the square of 2x squared plus 1. Instead of you taking 5 minutes completing the square, you just say it's already complete. So at that 5 minutes, you use it to work out D, where there is this question. That's the composition. That's how they combine the questions in the exam. If they put a simple one on that question, because they are saying all questions carry equal marks, on the very question, there must be something to compensate the time for those who have not picked that question. So that each question should have equal timing. So when the examiner says all questions carry equal marks, they also mean all questions cost the same time. You can't go on question 1 30 minutes and expect to go on question 2 5 minutes. No. They have said equal marks, meaning equal timing also. That's it. So that's how it's supposed to be. Very, very nice.
Excuse me, sir.
Yeah.
Can you please give us another example where the finding of this denominator, where we can find another denominator? I'm a bit behind here on finding a denominator.
Okay, let me add it in the source here. Yeah, this is.
So I'm kindly asking for the last slide.
Second last. Okay. Now the challenge is that in mathematics we have very few questions around binomial. Okay. So very few questions around the binomial. So we keep waiting. And when we meet it, we'll tackle it. This was identity number 4. Let's go to 5. Identity number 5 show that n0 plus n1 plus n2 plus n3 You keep going until you get nn. It's just the same as 2 to the power n. Show that. The proof of this is just getting the binomial. Since we said the binomial theorem is just a plus b to the power n, and we're expanding it in this way. So get it as it is. It's the only thing that has these coefficients in this order. So you put it as it is. B power n. Okay. Now, if you look at this thing very well, the only difference between this and our question is that ours, in the theorem, we also have an minus 1b, and in the question we only have the n0, n1, n2, n3 up to nn. So if we make a right choice of a and b, we may end up having a 2n. But that choice, we should bear in mind that that choice should not affect the n0, n1, n2, n3. So you know that the good choice here would be 1 plus 1. Where there's a, we put 1. Where there's b, we put 1. So that when we go on the other side, we'll have 1 power n. We'll have 1 power n minus 1, 1. We'll have 1 power n minus 2, 1 squared. We'll have 1 power n minus 3, 1, 3. We'll have 1 power n. But 1 plus 1 is 2. 1 power n is 1. 1 power, then 1 multiplied by n choose 0 is 2 n choose 0. 1 power n, 1 to n power is 1. Multiplied by 1 is 1. Multiplied by anything is that thing. That's the beauty of working with 1. It simplifies work. As required. Done.
Sir.
Hello.
I have a question. On choosing 1 there. What did you say can make someone like think to put 1? I didn't get that part.
So what can make you think of getting 1 and 1 is when you go to the theorem, you look at the way it is structured, compare it with your question. Our theorem would have been the question, except that where we have a plus b, there is 2 that side. The power is n. And when you come at the other side, you notice that the n choose 0, n choose 1, n choose 2, n choose 3, all the way up to nn. They're still there, but there is just no an, no an minus 1b, no an minus 2, b2, all the way up to bn. Those are silent there. So you look for a and b that can be silent, but there on both sides.
Okay, so.
Because we would have thought of having a 3 minus 2, having a 3 minus 1 to get 2 power n, but then 3 would appear. 3 power n, you have to evaluate it, but then you don't know what n is. So very complicated.
Too much.
Another identity. Identity 6. Let n be an even number. So that n0, n2, n4, nn is equal to n1, n3, n5, and n minus 1. We go back to a plus b power n, n0, an, somewhat. We've gone back. Okay. So you have an, n1, an minus 1b, n2, an minus 2b2, n3, an minus 3b3, n4, an minus 4b4. You can keep going up to n minus 1, a bn minus 1 plus nn. A doesn't exist there. It's a power 0 bn. So again, you look at your question. If this guy worked for 1 and 1, now we have something a bit complicated again, but we are told n is even. So even numbers have something to do with a negative. So let's try to get a to be 1 and b to be negative 1 and see what will happen. So we have n0, 1n, n1, 1 n minus 1, negative 1 while there is b, n2, 1 n minus 2, negative 1 squared, n3, 1 n minus 3, negative 1 3. Keep going up to n minus 1, 1, negative 1 n minus 1, all the way up to n negative 1 power n. But 1 minus 1 is just 0. Yeah. So unfortunate, power is gone. And my board can't write without power. I don't know how far I can go using the mouse. Okay. So you should be able to finish up this, because you can see that now you have 0 power n, and 0 power n is 0. So this side we have 0. Then these negative ones here will be where we have odd numbers down here. n1, n3, n5, n minus 1. All those parts there will be negatives. Then the 0, 2, 4, they will be positives, because negative 1 squared, like on the 2 part here, negative 1 squared is 1. So then we will have n0 minus n1 plus n2 minus n3 plus n4 minus n5. Then we'll take all the negatives the other side. Then they require to be the same. So then we'll be able to arrive at this. That's how the identity must come out there. Is that okay?
Yes, sir.
Okay. Identities. Okay, so we'll have to end our class here. I can't do anything else without power. I'll upload this, I think, immediate. No. After it has finished loading itself on Google. That's when I'll upload it.
All right, sir. Thank you.
Okay.